Section 7.4, Integration of Rational Functions by Partial Fractions. This is going to be a challenge for both of us because a lot of problems here are really long and complicated. Well, did I say complicated? I take it back. That's not a right word. They're just tedious. Elementary but tedious. Even worse. Well, let's begin with this motivational example given in the lower part of the screen in page 484 of our textbook. Let's begin with this rational function x plus 5 over x squared plus x minus 2. We have a linear function, linear polynomial in numerator and quadratic polynomial in denominator. It can be decomposed into two simpler fractions as we see in the left hand side, 2 over x minus 1 minus 1 over x plus 2. We can easily deduce the left hand side becomes right hand side by taking a common denominator as we see in the middle part. Now what if we want to find out the antiderivative of the right hand side, x plus 5 over x squared plus x minus 2, as we see here in this left hand side of the top of this page? Well, please remember this x plus 5 over x squared plus x minus 2 was the same as the difference of two simpler fractions, 2 over x minus 1 minus 1 over x plus 2. Consequently, we have antiderivative like this, two logarithmic functions. And this is typical way. Let's go back to the previous page. If you have a rational function as given in the right hand side, somehow we have to decompose the right hand side into the sum or difference of simpler rational functions and then take the antiderivative term by term as we see over here. We ended up with two logarithmic functions. Sometimes you're going to get logarithmic, sometimes you're going to get arctangent function. Well, that was a motivational example. And how do we actually deal with this kind of decomposition, which we call decomposition by partial fraction, by the way, is the big topic here. Before that, let's begin with rather trivial example number 1. This is rather trivial, and I do not consider this one as an important example because we don't have to deal with this decomposition here. All you have to do is just simplify this rational function by dividing the numerator by denominator and get a quotient and remainder, and we have simple expression here. How to divide is given in the left hand side in the blue font, the long division. This is something you're all familiar with from intermediate algebra or even elementary algebra in high school. So I'll just leave you with that. And if you take the quotient and the remainder over the denominator, then we are ready to apply all the antiderivative formulae term by term. What do you get? We have a polynomial function and a logarithmic function. Well, that was nice, but this is very special case. Special in that the denominator is very simple. It's a linear function. It just shows you that we can find out the antiderivative rather easily if the denominator is linear. And we expect nothing more than logarithmic function and maybe some polynomial functions. Personally, I haven't written this kind of problem for a long time in the exam because this is too trivial. But who knows, I may end up in very good mood and end up writing this kind of problem as a giveaway in the exam. So please do not completely disregard this kind of thing, even though this is rather trivial. Much better example is given in the next page, kind of like this. Evaluating this integral, x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. This is quadratic over cubic. And how do we handle this kind of problem? Well, the first thing you will have to do is to factor the denominator. As you saw in the previous example and the motivational example, we could decompose this complicated rational function into sum or difference of smaller, more manageable rational functions, and that was called decomposition by partial fraction, and that's based upon the factorization. So the first step is to factor it, and the denominator can be factored easily. It's a trinomial, so factor x out, and we have a quadratic, and then we have something like this. And then here is an ingenious step. We just set up an equation with undetermined coefficient a, b, and c, kind of like this. A over first factor, b over second factor, c over third factor. Of course, the order does not matter. And then our job is to find out a, b, and c, and we're going to have the decomposition. How in the world do we have this a, b, and c is rather difficult question to answer, and we're going to discuss it probably in next video or maybe even later. At this moment, we'll just accept it as is. A over the first factor, b over the second factor, c over the third factor, d over the fourth factor if there is something like that. And just use brute force computation to take the common denominator. So take the common denominator. Denominator is x times 2x minus 1 times x plus 2, and multiply out. The numerator will be kind of like this. And expand and then rearrange and do a lot of computation. And we are going to have this kind of expression. The coefficient of x squared is 2a plus b plus 2c. The coefficient of x is 3a plus 2b minus c. And finally, the constant term is minus 2a. Now, if we compare the coefficients, this x squared has to be the same as this x squared, so 2a plus b plus 2c has to be equal to 1. And comparing the coefficient of x, 3a plus 2b minus c has to be equals to 2, and negative 2a equals to negative 1, and what do we get? We have a system of linear equations. Solving this system of linear equations using all kind of techniques you went through in elementary and intermediate algebra, we're going to end up with a equals to 1/2, b equals to 1/5, c equals to negative 1/10. Consequently, we have this decomposition: 1/2, 1/5, and then negative 1/10. Finishing the antiderivative computation, we have these three logarithmic functions. Well, the last part, calculating the antiderivative, that wasn't too much of a deal, was it? All we have to do is just apply logarithmic function, logarithmic function, logarithmic function, except that here's 2, so divide by extra 2 in order to undo the chain rule, generating this 1/10 instead of 1/5, and that's about it. All the difficult part is finding out a, b, and c. And this textbook author did it in 1, 2, 3, 4 lines, but if you actually sit down and reproduce this, you're going to end up with far more lines actually. There's a lot of steps skipped here. Solving this linear equations, the system of linear equations, good luck. But then again, this is standard method, so how do we handle this kind of problem in given period of time in an exam environment? Oh my, that's a bit of a problem. I can write this kind of problem in homeworks, and yes, I do intend to, but in the exam, that's a very difficult story because of the time constraint. Consequently, I'm going to rely more upon a shortcut method, which I'm going to introduce through my notebook here. And here they are. The first, decomposition to partial fractions for quadratic denominator, number 1, when the denominator is monic and when the denominator is non-monic. Here, x minus r times x minus s generates quadratic denominator, but if you look at the right hand side, we have only x minus r, which will generate a logarithmic function, and x minus s, again the logarithmic function. This r minus s in denominator, or s minus r in denominator, those are just numbers, so they don't do anything significant. Consequently, we have these formulae, number 1 and number 2. So please write down these formulae somewhere and then practice a little bit and then try to use these. These can reduce your computation time significantly for some special cases. Special cases I mean by the denominator is quadratic. Next two formulae are about when the numerator has x. Again, we have these two formulae, and the derivation is pretty simple. Start from the right hand side and then use brute force computation to take the common denominator, and that's it. Again, let me open up, and then we have this formula for integration for something like that, and then that one. Well, let's see. Do we have enough time to do some example problems? I think we do, so let's move on to the example problems. In this notebook, for some reason, I just put all the example problems in the next section, next subsection here. How do we handle a problem like B? Well, the factor the denominator, x minus 2 times x plus 4, and then apply the formula over here, this one. What is r minus s in this case? Well, positive 4 minus negative 2, so we have 6. And then, of course, r minus s and s minus r, so we have just sign change. That's where we have this negative sign. Detail is left to the students, and then in the end, we have these two logarithmic functions. This kind of method gives you much simpler computation, and consequently, much safer computation. You know, each time you spend, each step you take, you're exposing yourself to possible mistakes. So if you take shortcut, if you do it accurately, it is that much safer. How about non-Money case? Okay, this is not exactly non-Money case because numerator is rather general quadratic. Okay, let's do that. This is rather comprehensive. So what we do, if you look at the formula over there, we have the formula for the constant, and we have a formula for x. So we'll have to use b and form d, and we can do it like this. Divide this integral or the integrand into two pieces, one with x, the other without, and then apply the formula for x, the formula 1d in the previous page, and use these AD minus BC, BC minus AD, and so on in appropriate places. Then you're going to get this computation over here, this expression. Do the same thing to this part, and then you're going to get this one. And the detail is left to the students. All you have to do is just go over there and then compare what is A, B, and C, and D, A, B, and C, and D, and then just put those numbers in and do the computation, and we're going to get this decomposition. After that, just routine computation, get those common factors together, and we're going to end up with this one after some further simplification, and put these two together, and you're going to get that one after further simplification. And we have two logarithmic functions as we expected. Mathematica actually will generate the same kind of answer like this. Much simpler than the textbook method. It doesn't work all the time, so be careful. It works only when the denominator is quadratic.